Hello, in this video I will be solving a problem on finding the nth root of a complex number, and this is from the 4th edition of MEI's A-Level Further Mathematics book. Let me start. Let z to the power of n equals a, where z equals r times open brackets cos theta plus I times sine theta close brackets, and a equals s times open brackets cosine of phi plus 2 pi k plus I times sine of phi plus 2 pi k close brackets, where k equals 0, 1, 2, 3 up to n minus 1. However, note that it will be useful to use negative integer values of k to obtain some of the nth roots, and this approach will be taken here. Z to the power of n equals r to the power of n times open brackets cosine of n times theta plus I times sine of n times theta close brackets. This is by De Moivre's theorem. Now, equating the line terms of z to the power of n and a will give us r to the power of n equals s, and n times theta equals phi plus 2 pi k. Therefore, we can write this as r equals s to the power of 1 over n, and theta equals pi plus 2 pi k all divided by n, where the domain of the argument z is equal to negative pi to positive pi. Based on the information given in the question, the complex number a may be written as a equals minus 4 plus I times 0, and a has modulus s and argument phi. Therefore, s equals to square root of minus 4 squared plus 0 squared, which is equal to square root of 16. Therefore, s equals to 4, and phi equals to arctangent of minus 0 over 4. Now, to determine the value of the argument of a, let me show the complex number a on an Argand diagram. From the Argand diagram, it can be seen that argument of a is equal to pi radians. Therefore, phi equals pi radians. Now, using this information, values of theta to obtain the fourth roots can be obtained as follows. N equals 4 and phi equals pi radians. Therefore, for k equals 0, theta equals to pi plus 2 pi times 0 over 4, which is equal to pi over 4 radians. For k equals 1, theta equals to pi plus 2 pi times 1 divided by 4, which is equal to 3 pi over 4 radians. Now, if k equals 2 is used to obtain the next root, the value of theta obtained will be greater than pi radians, which will lie outside of the domain of the argument of z. However, if k equals -1 and k equals -2 values are used to determine the remaining two roots, then the values of theta obtained will lie inside the domain of the argument of z. Therefore, this approach will be taken here. For k equals -1, theta is equal to pi plus 2 pi times -1, all divided by 4, which is equal to minus pi over 4 radians. And for k equals -2, theta equals to pi plus 2 pi times -2 divided by 4, which is equal to minus 3 pi over 4 radians. Also, for n equals 4, r is equal to s raised to the power of 1 over 4. Therefore, r is equal to 4 raised to the 1 over 4, which is equal to square root of 2. Now, using the above information, the four roots may be written as follows in polar form and then in Cartesian form. If I now call the first root z0, then in polar form, z0 is equal to square root of 2 times open brackets cosine of pi over 4 plus I times sine of pi over 4 close brackets. This is equal to square root of 2 times open brackets 1 over square root of 2 plus I times 1 over square root of 2 close brackets. And this is equal to 1 plus I. And similarly, the second root z1 is equal to square root of 2 times open brackets cosine of 3 pi over 4 plus I times sine of 3 pi over 4 close brackets, which is equal to minus 1 plus I. The third root z2 equals to square root of 2 times open brackets cosine of minus 3 pi over 4 plus I times sine of minus 3 pi over 4 close brackets, which is equal to minus 1 minus I. And the fourth root z3 is equal to square root of 2 times open brackets cosine of minus pi over 4 plus I times sine of minus pi over 4 close brackets, which is equal to 1 minus I in Cartesian form. Now it's a good idea to confirm these results. First, let me check if there are 4 distinct roots. So z0 is equal to 1 plus I. z1 is equal to minus 1 plus I. z2 is equal to minus 1 minus I. And z3 is equal to 1 minus I. Therefore, there are 4 distinct roots. And in fact, these are 2 complex numbers and their conjugates. I also need to check that the sum of the 4 roots is equal to 0. Therefore, let me add z0 plus z1 plus z2 plus z3, which is equal to 0 here. Therefore, the sum of the fourth roots is equal to 0. The question also wants the fourth roots to be shown on an Argand diagram, and this is done here. As can be seen from the Argand diagram, all roots lie on the circle inscribed by the radius r equals square root of 2 and centered at 0, 0. Also, the fourth roots form a square shape on this Argand diagram. Another point to notice is that the angle between two adjacent roots is equal to pi over 2 radians. This brings me to the end of this video. Thank you for watching.